Welcome, students. Today we're going to look at inconsistent and dependent systems. Remember, when we were solving systems of equations with two equations and two variables, there were three possibilities for what the solution might look like. We could have a single solution, which happened when the lines intersected. We could have no solution, which happened when the lines were parallel. Or we could have infinitely many solutions when it turned out that both equations gave us the same line. We're going to see a similar sort of a thing when we're dealing with 3x3 systems of equations, and so I want to look at a couple of examples right now. First, we're going to look at one. We're going to solve the system of equations x plus 2y minus 2z equals 1, then 2x plus 2y minus z equals 6, and 3x plus 4y minus 3z equals 5. We're going to use row operations, or Gaussian elimination, just like we did before, but this time we're going to see something different occurring. So remember, when we want to use Gaussian elimination, we're trying to get our system of equation in triangular form, which means we want to get rid of these three terms. Now, we don't need to change the first equation, so I'm going to rewrite the first equation down here, x plus 2y minus 2z equals 1. Now, if we want to get rid of this 2x, we can do that by taking 2 times the first equation, which will give us a 2x here, and then subtracting the second equation from that. So we're going to take 2 times equation 1 minus equation 2. So that's going to give us 2x minus 2x, which gives us nothing. Here, if we take 2 times the first equation, we get 4y minus 2y. That gives us 2y. And then here, if we take 2 times negative 2z, that gives us negative 4z. And we need to subtract negative z from that. We know that subtracting a negative is the same as adding a positive, so that's going to become negative 4z plus z, which is going to give us negative 3z. And then when we look at the constant terms, 2 times 1 is 2, and when we subtract 6 from that, 2 minus 6 gives us negative 4. So we end up with 2y minus 3z equals negative 4. Now what we're going to do is we're going to get rid of the 3x down here. And the way that we can do this is by taking 3 times this first equation and then subtracting the third equation from it, because that would give us 3x minus 3x, which is 0. So here we've got 3 times equation 1 minus equation 3. When we do that, the x's cancel out. If we look at the y's, 3 times 2y is 6y, and 6y minus 4y is 2y. If we look at the z's, 3 times negative 2z is negative 6z, and then we need to subtract negative 3z, but again, subtracting a negative is the same as adding, so this is going to be negative 6z plus 3z, which is going to be negative 3z. And then for the constant terms, we've got 3 times 1, which is 3. And then when we take 3 minus 5, we end up with negative 2. So that gives us a negative 2 down here. So we've gotten rid of 2 of the 3 terms that we needed to get rid of. Now we need to get rid of this one right down here. And this one is pretty easy to get rid of. What we need to do is we need to take the second equation minus the third one. We can just take the difference of these, and that gets rid of that term. So we're not going to change the first two equations, so I'm just going to rewrite them. And then for the last one, we need to take the third equation minus the second equation, or the second minus the third, it really doesn't matter. Let's take equation 3 minus equation 2. In this case, 2y minus 2y is nothing, those go away. Negative 3z minus negative 3z is the same as negative 3z plus 3z, which is 0. And so really on the left-hand side of this equation, because everything cancels out, we're just left with 0. And then on the right-hand side, we've got negative 2 minus negative 4, which is negative 2 plus 4, which is positive 2. So we end up with 0 equals 2. Again, we need to put a 0 on the left because when we subtract these from each other, everything cancels, and we can't have a side of an equation that is blank. We need to put a 0 to represent that there's nothing left. So we get 0 equals 2, and we know that 0 cannot ever equal 2. This is never, ever, ever going to be true, and what this means is that there are no values of x, y, and z that make our original system of equations true, and so there is no solution to this system of equations. No solution. This is very similar to what we saw when we were using elimination to solve systems of 2x2 equations with 2 equations and 2 variables. Whenever we got an equation that was false, that told us that the original system of equations is never true. When we were dealing with 2x2 systems of equations, the reason this occurred, if we looked at the graph, was because we ended up with 2 parallel lines. Now, when we look at 3x3 systems of equations, things are a little bit more complicated, but I do want to explain why this might happen. When we have an equation like this in 3 variables, x, y, and z, and it's a linear equation, this actually represents a plane in 3 dimensions. We've got an x-axis, a y-axis, and a z-axis. We're in 3 dimensions. And so each of these equations represents a plane. And in the examples we've seen before, when there was one solution, it meant that those 3 planes all intersected at one point. However, when there's no solution, what that means is that there aren't any points that the 3 planes intersect in. So they're actually intersecting in 3 different lines. It's kind of confusing and very difficult to imagine in 3 dimensions because we haven't done any graphing in 3 dimensions or looked at anything like that. But there is a geometric explanation behind all of this. It's just that it's a little bit outside our grasp to actually look at it. You will see some of this if you end up taking Calculus 3, though. We look at different graphs in 3 dimensions. We look to see where different surfaces intersect each other. And it's really a fascinating part of the class. But it's just a little bit outside of what we're going to focus on right now.